We are very happy and delighted that we have with us today Professor Subir Sarkar from Rudolf Center for Theoretical Physics, Clarendon Laboratory, University of Oxford. So as I told that, he doesn't need any introduction, but, with his due permission, I would like to take few minutes to introduce him formally, because I can see there are many young students and postdocs today, they have joined for this colloquium.
Just 2 minutes, please, because I need more time.
Yes. So he did his BSc and MSc from IIT Kharagpur in 1974. And then he started his PhD in TIFR and obtained the degree in 1982 from Bombay University. Then he was a visiting fellow at CISA, research associate at CERN, then again visiting fellow at University of Oxford, then research associate at RAL, staff member, then he became the staff member of this Rudolf Peierls Center for Theoretical Physics, University of Oxford since 1990. And then he's working there, and he was the head of this particle theory group at this place during 2011 to 2019. And also he is an adjunct professor of he was an adjunct professor of TIFR between 2006 to 2009, adjunct professor of SINP between 2008 to 2013, associate of IPP Dhahram in 2011 to 12, associate of Niels Bohr Institute 2010 to 2020, and he is an affiliated professor at University of Copenhagen now, and also adjunct professor of RRI. Just let me say a few words about his research interests. So he has mastered himself in both the field of theory and experimental particle physics. So as far as theory is concerned, his research work lies at the interface of fundamental physics with astrophysics and cosmology, like dark matter, dark energy, inflation, cosmic microwave background, neutrinos, other relic particles. And I would like to mention that he is a strong supporter of our India-based Neutrino Observatory project, and he is helping us in many ways to promote the physics of this project and also for the science outreach of this project. And he is an active member of Peierls Observatory, IceCube collaboration, Cherenkov telescope array. And today I hope that he is mainly going to talk about these observatories and the fundamental physics that he is involved in with these experiments and the landmark discoveries that he has made or he was a part of, while working on these experiments. So with these words, I would like to request Professor Subir Sarkar that please, tell us the excitement that we are having now with astrophysical neutrinos.
Thank you, Sanjeev. And thanks to all my collaborators in this experimental collaborations you mentioned, and also, of course, my theoretical collaborators. So I'm going to report on work done over quite a number of years. And because you asked me to keep it at an accessible level for students, I'll try my best to do that. So the first thing to say is that cosmic neutrinos are quite difficult to hunt for, and to do so you often have to go to some rather remote and beautiful places in the world. So this picture up here is the Pampa Amaria in Argentina, and that which Luis Anchodokwi is a Argentinian colleague and we are installing electronics on top of one of the tanks of the Peierls Observatory. There are 1,500 tanks like that spread through the Pampa over thousands of square kilometers. And the reason why you're doing that is because this tank, although designed to detect cosmic ray air showers, it turns out is also possible to look for neutrinos with it, because they are raised above the Pampa by, as you can see, a couple of meters, really to stop the cows from getting at the electronics on top. That's why they were designed to be that high. But that means that they have a little solid angle towards the horizon, So you can look for air showers which are coming along the surface of the Earth, very close, skimming the horizon, which means that such things should have passed through several thousand grams of air, and no cosmic ray can penetrate such a depth. Only a neutrino can penetrate such a depth and have an interaction close to the array. So that was part of the search for neutrinos that we were doing at the Peierls Observatory. However, to date, there have not been any detections of neutrinos. The search is still continuing. What has been most successful is another experiment that I was fortunate enough to be involved in right from its construction in 2004. This is the IceCube Neutrino Observatory, which all of you have heard of, which is buried over 2 kilometers deep under the South Pole. And this experiment did make the discovery of high energy cosmic neutrinos, has interesting indications of a possible source. But today my talk will be focused not on the astrophysics, but on the particle physics that we hope to learn from this kind of astroparticle experiments. So this tank, as I said, is one of the tanks of the Peierls Observatory. There are 1,600 of these tanks. They're filled with pure water, and each one is viewed by 3 photomultipliers facing downwards into this tank of pure water. And what they do is detect the air showers that pass through them. And in fact, you can see a artist's impression of what an air shower hitting the pampa looks like. By the time it hits the ground, it's spread over many square kilometers. And this particular detector is spread over several thousand square kilometers so that it can, in fact, see the highest energy particles. And it was Alan Watson and Jim Cronin who dreamt up this experiment and kindly invited me to join. This was back in 2003. I'm no longer involved with Auger. I left in 2012. But the reason I got involved was because I actually had started my research career at TIFR, as Sanjeev kindly mentioned, doing cosmic rays. So I have a long interest in the topic. Now, these detectors are spread through the pampa. Each dot represents one of those tanks. And surrounding them are 4 fluorescence detectors, which look like that. They're usually on top of little hills, so they can have an uninterrupted view. And these are all closed up because what's inside them are 4 Schmidt cameras, very sensitive cameras because they have at their focus the CCD detectors, actually they're photomultipliers, but they can see the track of the shower across the sky, and I'll just describe how that happens. So using these, we can see the highest energy particles in the universe, because when such a particle comes in and creates an air shower, the air shower hits the ground and triggers those detectors on the ground. And the shower in the atmosphere is also tracked by observing the fluorescence radiation that is excited when the ionization excites molecules in the atmosphere. And this particular shower was detected by all 4 of the fluorescence telescopes. So you can imagine that its incident angle was very precisely identified. And by tracking along the shower, you also get a calorimetric measurement of the total energy of the shower. And this particular shower had an energy of 10 to the 10 GeV. So that number is correct. We are used to high energy collisions at, say, the Large Hadron Collider, where you have got up to about 10 TeV. So that's about 10 to the 4 GeV. This is 1,000,000 times higher than what the LHC is doing, right? And it's really something to be doing a shift when an event like that happens, and you actually see sort of in front of yourself that nature is actually capable of accelerating particles to such humongous energies. Now, the air shower is triggered by an incident cosmic ray, which hits a molecule in the atmosphere. And this is a simulation by Drescher at Frankfurt. And the color coding will show you the development of the shower. It's a very nice semi-analytic model that he has got, which shows you separately the photons, the electron positrons, the muons, and the hadrons, color coded as indicated. So in the first collision, that's when the center of mass energy is very, very high, much higher than anything we can prove in the lab. But then, of course, there are multiple subsequent collisions. There is the cascading, fragmentation. And by the time the shower hits the ground, there are about as many particles in it as there are galaxies in the universe. So you can imagine that simulating such an object is quite a challenge. You have to use various numerical techniques to thin the shower and essentially track it from a center of mass energy which might be as high as 100 TeV down to MeV energies, which is so basically you have to have everything we know about nuclear and particle physics involved in modeling that shower. And because, of course, we don't have any direct knowledge of interactions of physics beyond the LHC energy, say, 10 TeV, and until the LHC, we didn't really know about interactions beyond much smaller than that, 1 TeV. So these air showers were always hard to model, and there were many, many uncertainties. But when LHC first turned on, there was a surprise. It turned out that the energy estimate we make by tracking that shower and observing its development in the atmosphere, it reaches a peak of brightness and then fades off. And this maximum, which is called X max, this is in fact an indicator of what kind of a particle it is. A photon would give a shower profile quite different from that of a nucleon, and a proton would give one somewhat different from an iron nucleus, although not very much. When this shower hits the ground, we measure the activity as a function of the distance from where the shower hit from the core. And the lateral distribution is also quite nicely described by, this is a form, a parameterization of the activity, which is according to Tom Geiser, which fits the data quite well. And what we do is you measure the activity at a certain point. For example, in this example, 1 kilometer from the core of the shower, and that turns out to be a pretty good measure of the total energy in the shower. And we know this because when we cross-correlate the energy which is estimated via the Monte Carlo from the ground array versus the direct calorimetric measurement in the measurements by the air fluorescence technique, then the two correlate very well. However, we can't use this technique all the time because you need the sky to be totally dark to see the faint light due to the shower. It's like a 40-watt bulb which is whipping across the sky at the speed of light, tens of kilometers away from you. So it only works about 10% of the time, and that is why you have to go to such a remote place to get really dark, moonless nights. But the two energies do correlate. And when LHC first turned on, it turned out that these Monte Carlos that we are using to estimate these energies, which had always been, considered a little suspiciously, because obviously you are exploring physics beyond the range that laboratory experiments can probe. However, they turned out to be, in fact, very much on top of the data. In fact, they gave a better fit to the LHC data than the standard collider generators like Pythia and so on. So Pythia, of course, was retuned to the first LHC data and now gives a much better fit. But I must say it was a pleasant surprise to all of us that the air shower Monte Carlos did so well. Observe that what is plotted here is the multiplicity or whatever quantity you're interested in versus the pseudo rapidity, because these collisions are essentially in a frame that is highly boosted in the forward direction. These are not colliders. You have an incident high energy cosmic ray hitting a stationary atom or molecule in the atmosphere. And therefore, the cosmic ray experiments sample very large pseudo rapidities. And of course, at the LHC, the detectors like Atlas CMS, they normally do not explore that kinematic range. But there have been special forward physics experiments set up at the LHC, like LHC-F for LHC forward, or Totem and various other experiments, which have also tried to make measurements which in the case of the LHC would be almost straight down the beam pipe. So you can imagine why it is so hard to do experiments there. But in that sense, what we do in air shower physics is literally orthogonal to what's being done at colliders, because there you are interested in very rare uh, high PT, transverse events, and you essentially ignore most of the data that is going in the forward direction. Here we are restricted to looking at what is coming in the forward direction. Now, the question, of course, is how does nature manage to accelerate particles to energies a million times higher than the LHC? And
So
a very
Shobita, I
simple,
have one question.
yes,
So when you are trying this connection between collider environment with this extreme environment of cosmic air shower, so
yes.
still we have a desert like 1 million in the energy, right? You mentioned that at
Well,
most
not a million in the beam energy, but only a factor of 10 to 100 in the center of mass energy.
okay, so like in collider you have like 10 TeV, but here you are
Right,
talking about like 10 to the power 10 GeV, right?
right.
You
But when
mentioned.
it hits a nucleus, let's say of 10 GeV, and you take the square root, it comes to about 10 to 100 TeV.
Okay.
Right?
So
So
this
it's not that
extrapolation is
far
not
off.
that difficult.
No, the extrapolation is difficult because you don't know what's going to happen in there. All the new physics that you hope might exist, physics which might interfere with this. But this is that itself is worth several talks. I was just trying to give you a bottom line, which is that the collider Monte Carlos like QGS jets, Sybil, this is a QCD motivated one, or EPOS, which is actually very good at modeling heavy ion collisions. These all turned out to give a very good description of the first LHC data. And there is the proof of the pudding, as it were, that you can trust them. Because until that time, there had been some skepticism as to how well we can, in fact, estimate the energies of these events. Okay.
Thank you.
So I don't. So thanks for the question, but I just wanted to highlight that there are uncertainties, but they are not a problem. So with regard to how nature accelerates such particles, a point that was made by Michael Hillas a long time ago was that forget about how to accelerate them. Just to contain a particle of that energy, you know that you need a containment volume which is sufficiently big for a given strength of magnetic field. So if you plot the field versus the size, then a particle of a given energy, say that particle that I just showed you, this is 10 to the 11 GeV, 10 times higher. This is the highest energy particle ever seen. To contain that, you would need to lie on the red line. And you can see that most of the usual suspects for sites where cosmic rays might be accelerated would find it difficult to even contain a particle of that energy, far less accelerate them, in which case you have to also worry about radiation losses, efficiency, and so on. A very simple way to see how demanding such a task is to ask, supposing you gave me LHC technology, 6-7 Tesla magnets, all the engineering, all the alignment, the deflectors, all the stuff that goes with making such a amazing machine. What would it take to make a particle of that energy? And the answer is that you would have to make a ring which is a little bigger than the FCC. It would have to be about the orbit of of Mercury. Okay, so nature somehow manages to do this in objects like active galactic nuclei, such as these are the black holes that are at the centers of most galaxies, and some of them are active and shooting out beams of plasma. Sometimes those beams are aimed towards us, and we call them blazars. Or it could be gamma ray bursts, which might have very high magnetic fields. They are compact objects. They also implicate compact objects like neutron stars and black holes. Or it could be very extended objects like the large, huge jets that are coming out from this active galactic nuclei and form radio galaxies. So uh, you can see that even these objects would find it challenging to accelerate a particle of that energy, but they are our most likely candidates. Now, whatever the sources are, what we can actually detect at Earth is the cosmic rays that come from them. And this is a summary of the spectrum of cosmic rays, which you have seen before, uh, starting at about a GeV and going all the way up to 10 to the 11 GeV, as I indicated. And there are, of course, cosmic rays at lower energies, but they are affected by the solar wind, and which kind of pushes them out of the solar cavity, and their flux varies a lot over the solar cycle. And we normally look at only these relativistic particles. And here we can see that they are roughly modeled as a power law, which is not very far from the e to the minus 2 form, which theoretical arguments about acceleration by stochastic turbulence or shocks might lead you to think that that was a likely spectrum. This was first formulated by Enrico Fermi. And there are, of course, interesting structures on top of that. For example, there is a bend here called the knee. There is another bend here upwards, which we call the ankle. And you can see also from here that the center of mass energies that we just talked about at the lab only reach up to here. And we are going many orders of energy beyond. But the center of mass energy is only about a factor of 100 beyond. Now, we don't know what the sources are. Supernova remnants can accelerate particles up to about here. And we have seen the pi naught decay gamma rays from supernovae, which have been created by the pions that are created by interactions of the cosmic rays with ambient matter and radiation. And what we are after in this talk are the neutrinos that result from the decays of the pions and muons and so on. And of course, if you make neutrons, they will also give you anti-electron neutrinos. Now, the reason why I have marked here galactic and extragalactic is that these particles are of such high energy that they cannot be contained by the galactic magnetic field, but we see them as isotropic rather than only along the Milky Way. So therefore, the sources must be isotropically distributed around us and presumably extragalactic. Whereas up to here, they could be galactic. There is ongoing controversy about what is the origin of the particles in between the two. It could be a combination of both sources. As you can see here, for example, from pi decay, you have muon neutrinos and electron neutrinos, and you know this process is also happening in our atmosphere, and you get 2 muon neutrinos for every electron neutrino. But when this happens in a distant source, by the time they get to Earth, the oscillations have averaged out and the flavors have been equilibrated. So you expect roughly equal parts of each flavor, including tau neutrinos, and this will turn out to be important. Note also that you make neutral pions at about the same rate as the charged pions, and these will give you gamma rays. So this is a very interesting way to calibrate the neutrino flux, because you expect a similar flux of gamma rays. Of course, their propagation is different, and that you have to take into account according to whether they are within the galaxy or coming from very far away. And the final remark I want to make is that the fluxes at this high energy end are very, very small, which is why the Auger Observatory has to be so big in order to get any events at all. Nevertheless, these collisions are happening all the time above
so,
us.
Shubhita, just to disturb, so will
Yeah.
you take questions now, like in these slides which are coming now?
Yeah, you can ask questions as you go along, but can I ask, I see we are already at 12 o'clock. I mean, are you
So we
expecting
can
me
take
to?
questions at the end.
No, I'm happy to take questions as we go along if you allow the time for it, because then I can't finish at 12:30.
Time
Okay,
should not
please.
be that.
Then
So there
please
is a
ask
question.
questions.
There is a question from Arjun that,
Yeah.
sir, when you are talking about extragalactic sources,
Yes.
can we find their exact sources?
No, well, this will become clear later. We have not yet seen any extragalactic source of cosmic rays. We have seen possibly one extragalactic source of high energy neutrinos, which would also presumably be a source of cosmic rays. But even that is not a fully definitive detection. It was only 3.5 sigma. Okay, so some things will become clear as I go through the talk. So perhaps that kind of question can be reserved till the end of the talk.
Okay.
But if you have an immediate question on something I've said in my slide, which is not clear, then please ask right away. Okay? Thanks. So as I was saying, the center of mass energy from these collisions is indicated up here in this nice slide, which I got from Ralph Angel. He's the current spokesperson of Peierls Observatory. And you can see here that the LHC is around here, around 10 TeV, and the center of mass energies of the collisions that cosmic rays have with particles up in our atmosphere go up a factor of about 20 to 30. But note that the flux is falling off very rapidly, and I've already multiplied these data points by e to the 2.5. Otherwise, it would be dropping like a stone. Okay, so the fluxes are very, very small here. The luminosity is extremely small, and that is why it is this can only be complementary to laboratory physics. It cannot replace collider physics, never. And besides which, these collisions are happening up there where there are no foci detectors like ATLAS or CMS to study them. But the attraction of studying these events is that they do reach up to energies that we can't ever do on Earth, and they might give us some interesting complementary information. So this is what I indicated earlier. Now, when you get up to energies of the order of about 510 to the 10 GeV, the protons are energetic enough that in their frame, they will see a cosmic microwave background photon, which has an energy of about milli-electron volt. They will see that photon boosted to an energy of about 100 MeV. So that is the energy you need to make a pion, and you can therefore excite the proton to the delta 1232 resonance, which results in copious pion production. And that energy loss is so prohibitive that the spectrum should cut off at this point. We should not really see any events beyond that energy. And indeed, Auger has confirmed that there is a cutoff at that point. Earlier, there were events which were claimed beyond this energy by the Agasa experiment in Japan, but they turned out not to exist. Now, when you look at photons instead of particles, there again you have a huge range of energy over which you observe the universe. So, of course, with our eyes, we see the optical universe, but that's only because our eyes have, the wavelength range has been decided by the wavelength range in which our sun emits energy. When we discovered other ways to look at the universe, so for example, when we discovered radio technology, we opened up the radio universe, and similarly with infrared, ultraviolet, X-rays, gamma rays, and so on. Most of the energy is at microwave energies. This is the energy per unit energy interval, and you can see it's dominated by the cosmic microwave background. But there are photons of all energies extending up to gamma rays, which at around 10 TeV or so, they would start getting attenuated on the intervening photon backgrounds, and therefore we cannot see them anymore. So there will be a window here where we can't actually explore with gamma rays. Cherenkov telescopes mainly look at nearby objects. But with cosmic rays, we can go up to 610 to the 10 GeV before they're attenuated, as I said, through this so-called Greisen-Zatsevin-Kuzmin process on the cosmic microwave background. But neutrinos interact, of course, far more weakly, and therefore, essentially, we can look at the entire universe at all neutrino energies back to about a redshift of 10 to the 12. That is the time when the universe became dense enough and hot enough that neutrinos themselves came into thermal equilibrium, and will have a sort of a photosphere or neutrinosphere. Just like we have the last scattering surface of the cosmic microwave background, there will be a similar one for the cosmic neutrino background. But certainly anything within a Hubble volume, we can see with neutrinos. Now, how do you actually detect all these things? So I've already shown you a picture of a detector. Here is a nice slide from Thomas Losey, which illustrates what happens when a shower comes in and hits the Earth. So we have detectors on the ground, which could be, cheap water Cherenkov detectors like in Auger, or scintillators, or more expensive detectors for hadrons. And they have to cover a very large area and therefore have to be relatively cheap in order to do so. Now, the air shower also generates, at this end product, it generates muons, which have a very long range. And in fact, you know that you put a cosmic ray detector in your lab, you can hear the muons going through. You can see them in a cloud chamber, or you can hear them triggering your detector. It's good for demonstrating to schools. But they also emit Cherenkov radiation in the forward direction, because these particles are moving faster than the speed of light in air. And air Cherenkov telescopes, imaging telescopes like MAGIC and Veritas and HESS, look for these. And now we have the forthcoming Cherenkov telescope array, in which India is also involved, which will study these in great detail. And you could also have detectors deep underwater or under ice, because that is helpful for detecting these muons going through. And as I mentioned earlier, the ionization along the shower excites air molecules which emit fluorescence radiation in the ultraviolet, and that can be detected by, after suitable wavelength shifting, by these fluorescence cameras, such as I showed you in Auger, which provide a calorimetric measurement of the shower. And then you could also have events coming up through the Earth, which are triggered by neutrinos. And these have to be looked for against the background of neutrinos which are being generated in the atmosphere from these cosmic ray interactions. And they, of course, come from all directions, because neutrinos, the Earth is relatively transparent until tens of TeV. And there is an even bigger background of muons which are coming from these atmospheric interactions. So it is going to be quite hard to look for these primary neutrinos. But we are doing that with IceCube and Antares and other neutrino telescopes. What is under development right now is radio detection, because these instruments have to cover a huge area and the cost mounts up. You have to develop a technique that can monitor very large volumes or areas at a relatively cheap cost. And radio detection is the most promising. So there are several experiments currently using the radio technique. You would have heard of Anita, which flies on a balloon around the Antarctic. And then there is also the experiments Ara, Ariana, and so on. And there are very optimistic future proposals like Grand, which would be in China, and so on. So let me come to the bottom line. We have, of course, made huge advances in particle physics by constructing amazing machines like the Large Hadron Collider, and that has achieved 13 TeV center of mass. But as I've already emphasized, a cosmic ray interaction in the atmosphere can generate center of mass energies, 10 times higher than that. But observe that the luminosity is pretty pathetic. The rate is less than 1 per day, even in a experiment as large as the Peierls Observatory. So what is more interesting is to ask, supposing I want to look for new physics, can I do that in cosmic ray interactions? The answer is no. It would be very difficult, because the typical hadronic cross-section is of order the inverse of the QCT scale square, right? So it's actually a million times higher than the kind of cross-section for new physics, which would be at least inverse TeV square, right? And therefore, it would be extremely hard to study hadronic collisions with such precision that you can pick up some new stuff at a 1 in a million level. But if you look at neutrino interactions, because they are so weak to start with, a change in the cross-section due to new physics might be easier to spot. And that is the philosophy behind using cosmic neutrinos to study, to look for new physics. Now, where are these neutrinos? How do you know their beam? Cosmic rays we can measure using Peierls Observatory and other such experiments. What about neutrinos? Well, those Greisen-Zatsepin-Kuzmin interactions on the CMB should generate neutrinos. This is called the guaranteed neutrino flux. But of course, nothing in life is guaranteed except death and taxes. I think Benjamin Franklin said that. And in fact, it turns out that if the primary particles are not protons but heavy nuclei, this flux would be reduced quite significantly. Nevertheless, it is one of the primary targets for large neutrino observatories. The particles that are being seen in cosmic rays came from somewhere. So whatever their accelerators are, some typical suspects are active galactic nuclei, gamma ray bursts, etc. They would be generating neutrinos as the cosmic rays are getting out of the source. and one can get an estimate of that flux by normalizing to the observed flux of cosmic rays. This also has many uncertainties. For example, it depends on how much energy is there in those cosmic rays. And because it's a steeply falling power law, that depends on the lower energy down to which they extend. That's the question is, at what point do extragalactic cosmic rays start dominating over galactic cosmic rays? And that's the thing that I indicated earlier, uh, uh, could be the ankle or it could be an energy below that. Then there is more exotic possibilities. People have speculated that you could have top-down sources, in other words, some relics of the early universe, topological defects, super heavy dark matter. And this was mainly motivated by the fact that Agasa saw events beyond the energy at which they could come to us from any distance, because their mean free path would be quite small on the cosmic microwave background. Now, let me just take one slide to show you that we do make progress in this field. These ideas are tested, and this particular model has been ruled out by the Auger Observatory in the following way. We look to see if the primary cosmic rays are photons or nucleons, because the decay of super heavy particles should dominantly create photons. And it turned out that, in fact, the primary cosmic rays are not photons, so therefore they cannot be resulting from any top-down process. Now, the motivation, as I said, was that Agasa saw these events beyond the GZK cutoff. And if you see events on the sky which are coming from every direction, but cannot have been generated very far away, then the most attractive location for their origin is something in the galactic halo, because the galactic halo is also roughly symmetrical, spherical about us. And it is possible that the dark matter is constituted of very heavy particles. And there has been some theoretical studies saying that you can actually create very heavy particles at the end of inflation when the Hubble parameter is very large because of the changing gravitational field. And they even had a catchy name, Wimzillas, that Rocky Kolb gave them. And the picture would be that these particles are in the halo and they're decaying, and we are seeing the cosmic rays from them at Earth. However, this possibility is testable, because the energy spectrum would then be determined by something we can calculate. It would be determined by fragmentation. So, in other words, when the particle decays, say to partons, then they initiate a QCD shower, which can be modeled using the same tools that we use to model showers in the laboratory. In fact, since you are going to energies much higher than the laboratory, you have to do it by evolving the fragmentation functions that you measure for known particles like the Z boson. You take the fragmentation of the Z boson and then you evolve it to a center of mass energy of whatever it is, 100 TeV, or in this case, it's a 10 to the 10 GeV particle. And you do that by using the DG-Lap equations to evolve the fragmentation functions. The answer is that the spectrum can be calculated, and it is of the right shape to match the events that we're seeing. But the clear expectation is that photons should outnumber nucleons. And this is something that we know is true of all such showers. However, when we looked for this in Auger, the depth of maximum of photons is very different from that of nucleons. And so it is possible to look for the composition, just trying to distinguish between photons and nucleons. And we are able to set an upper limit on the photon fraction, which, as you see, is well below the expectation from this theory. And therefore, this rules out all such top-down models. And more recently, the same idea has been proposed to explain some of the events that have been seen by the IceCube detector, which have been ascribed to the decay of multi-PeV mass particles. This has not yet been definitively ruled out, because the photons in that case may not be able to propagate through the galaxy. They would scatter on starlight. But you would still expect an anisotropy, because we are not at the center of the galaxy, we are off center. So you'd see more events coming from the center of the galaxy, that direction. And that dipole anisotropy can be looked for, but that would require a minimum of about 500-600 events. And we still don't have that many events to rule that possibility out. The next source of neutrinos then is the sources of cosmic rays themselves. And as I've already said, we expect them to have some power law spectrum from simple theoretical considerations. And by calorimetric argument, we can relate the energy in neutrinos to the energy in cosmic rays, because some fraction of the cosmic rays will deposit their energy in neutrinos. So it's like a cosmic beam dump. And of course, there are many uncertainties in this argument because we don't really know the spectrum, we don't know the energy cutoff, but we can nonetheless get an estimate of what sort of flux to expect. And this is expectation which was initially presented as an upper limit by Waxman and Bakal, but we can actually make it into a tangible expectation by putting in real numbers. This is, of course, uncertain because we don't know how much energy is contained in extragalactic cosmic rays. That depends on at what energy they start overtaking galactic cosmic rays. And then we have this so-called guaranteed flux, as I mentioned.
Question, Subir?
Yes, please.
Yeah, I was just wondering. I think I saw some works earlier about this extremely high energy cosmic rays from rotating black holes close to extremal limit by Penrose process.
Yes.
If that is that doesn't have to be accompanied by neutrinos, right? Then if that process is
No, any place where the particles that are being accelerated will interact with ambient matter and radiation, you will get neutrinos, right? So unless you have a rotating black hole making high energy protons with nothing near it, and we know that no black hole is naked, they'll always have an accretion disk, it'll be matter falling onto it. So I think the same argument works.
I see. Okay, thank you.
Right. So then we come to the cosmogenic flux, which we have already discussed earlier. And this is something which extends up to the highest energies that cosmic rays themselves have. So it's particularly interesting to look for it. And here are some early estimates made of the cosmogenic flux. The two peaks are because this is coming from this chain here, whereas this is coming from the neutrons, which are giving you anti-electron neutrinos. But for detection, this is much more interesting because muon neutrinos are easier to find than the electron neutrinos. But there are many uncertainties because we don't know the spectrum, we don't know the evolution of the sources with redshift, and so on, so on. We noted, however, that it is possible to use the gamma rays that are also made in this process, because the same process will also make neutral pions, which will give you gamma rays. And Marcus Allers led us in a work where we calculated if we have a primary beam of cosmic rays like that, then what would be the concomitant production of gamma rays from the pi knots, which are made in the GZK process, and that would then be this blue line. So all we had to do then was to insist that this should not exceed the diffuse extragalactic background of gamma rays that had been observed by Fermi, which are these data points here. And by normalizing to that, we then normalize the neutrino flux, which is shown here as these green lines here. So we can therefore get a constraint on the cosmogenic, as it is called, neutrino flux via the concomitant gamma rays that would be produced in the same cascade. And this means that many of the uncertainties about their cosmological evolution, etc., can be circumvented. Okay. Of course, if the primaries are heavy particles, then the cosmogenic flux would be a lot smaller. So what now really matters is what is the proton fraction in the highest energy cosmic rays. And in fact, with Luis Anchodokwi and Marcus, we pointed out that actually we could put a constraint on the proton fraction simply from the fact that the neutrino flux had to be below the upper limits which were then present. Now, the same argument has been extended by Marcus to make the following point, which is relevant in the context of what I'm about to say next. Here are the cosmic rays, here are the photons, and now we have discovered in the energy range in between cosmic neutrinos. And there are several synergies here which are worth pointing out that described in the caption to this figure taken from this review by Marcus and Francis Halzen. But what they're saying is that these ultra-high energy cosmic rays will give you this cosmogenic flux, but the cosmic proton spectrum, which would have gone down to lower energies, not just the ones responsible for the highest energy cosmic rays, would have created also neutrinos to which one can put a calorimetric limit. And it's interesting that the neutrinos that you observe are bounded by that calorimetric limit. Okay, this is not the Waxman-Bakal bound. This is a calorimetric limit based on the proton flux at much lower energies. And of course, similarly, you could ask for a connection between this this blue line here, which is the thing that is being compared with the gamma rays. Okay, so the isotropic gamma ray background is shown as the data points, and this line here would be the emission that is connected with that. Okay, so you can see here, therefore, that all these things are plotted as E squared times the flux. So it's a measure of the total energy content, and all these energy contents in these components are comparable. So it's clearly trying to tell us something interesting about the sources. But my topic today is not the astrophysics. As I said, it's the particle physics, and I see that I've already taken up most of my time, so I'll go rather quickly through this. How do these neutrinos interact in our detector or anywhere? Well, at energies above a few GeV, which is the focus of most neutrino experiments today on Earth, because they're studying low energy oscillations, but we are interested in high energies. And beyond a few GeV, it's deep inelastic scattering. And this process is mediated by the W. So here you have the W propagator, and of course the weak coupling. And then you have to take into account the internal structure of the nucleon that they are interacting with. So, and that is quantified in terms of the structure functions, and that's related to the Photon distribution functions inside these nucleons. And as you see, if I increase the momentum transfer, then this quantity goes down. But if I increase the magnitude of the Photon distribution functions, then it goes up with the energy, with the momentum transfer. And most of the contribution to the cross section, if you look at this, will come from when Q square is of order mw square. And the fraction of the momentum, the Bjorken x, which is carried by this particle, is just mw square over the mass of the struck particle times the energy of the neutrino. So as the energy of the neutrino goes up, this is going to become smaller and smaller. Now, one can write down these at leading order in a closed form in terms of the content of the nucleus, the Photon content. But of course, at higher orders, there are complex corrections, and you can't write it down so simply, but you can calculate them numerically. If you go to next to leading order, there is only about a 1.5% change, so that's not so important. Now, as I mentioned, as you go to higher and higher energy interactions, so this is at s of 10 to the 8 GeV square, this is at s of 10 to the 11, and you can see this contours are showing you where the contribution to the deep inelastic scattering cross-section is coming from. So 50% is within this contour, 90% within this contour, and so on. And you can see that it has gone from, as you go from 10 to the 8 to 10 to the 11, this has pushed down to much smaller x values, right? So in order to understand how neutrinos interact at very high energies, we have to know what these Photon distribution functions are down to as low x as you can measure, right? It turns out that for energies up to PeV, the measurements which were made at the Hera accelerator by the H1 and Zeus experiments are adequate to provide PDFs in the necessary kinematic range. If you go to energies beyond that, then you have to evolve them using the standard DGLab formalism and perturbative QCT. So it's getting a bit technical. I'm just trying to keep it at a simple level just to give you the gist of it. Now, these experiments actually made a very striking discovery that, we tend to think of the proton as made out of up and down quarks, and so they are, these valence quarks at, small values, at sort of large values of the Bjorken x. But as you penetrate to very small Bjorken x, you can see that essentially these experiments discovered that the nucleon is essentially made out of gluons. This is the gluon distribution function. And it has been multiplied by 1/20 to bring it down to a level where you can actually see it next to the valence quarks. Otherwise, it would shoot up like that. Now, this was quite unexpected. And this has interesting implications for high energy neutrino interactions, because they would be sensitive to this Photon distribution function at low x. And of course, these measurements are in perfect agreement with perturbative QCD. Even at low x, they actually fit quite well, surprisingly so, because you'd imagine, for those in this audience who know these things, there are log 1 by x corrections, which would be expected to be quite large, and you would need to do something called the BFKL resummation. But although there is an indication that that does improve the fit to the data, it is by no means something that is yet a major effect. So basically, perturbative QCD works a lot better than people had expected. And this plot is showing you the range of Q square and X that have been explored by previous experiments. And you can see from the previous slide that we need to go to much lower X and high Q square in order to get to the regime that is relevant for neutrino experiments. So there is a very interesting synergy between these two, and proposed new colliders like the LHEC and so on would be very relevant in this connection. Basically, a neutrino nucleon interaction, the closest thing to it on Earth is a electron-proton collider. Okay, we don't have to care. We have neutral particles, but the process is the same. Now, the cross-section that we found using this was indeed different from what was being used earlier. And this is important at high energies. Then there are these effects that I mentioned, which might be relevant at those energies. But surprisingly, the fit is not too bad to the data, even at the basic unscreened perturbative level, without worrying about all these saturation effects and so on. And of course, the calculation agrees with direct measurements at the energies that have been made in accelerators, which is up to about 200 GeV. Now, if you want to see these neutrinos, knowing the cross-section, how big a detector do you need? So you do your back of the envelope calculation, and you find that if you plug in Avogadro's number and typical density of material and the cross-section, then you need something like a kilometer cube of detector, right? So this is why neutrino telescopes need to be so big. They could be water or ice, and what you look for is the tracks that are left by not the neutrino, but the charged particle that it creates in the interaction, like a muon, which has a huge range at these energies. And the muon would be traveling faster than the speed of light in the medium, in water or ice, and would therefore put out a Cherenkov light cone. And if you instrumented this volume with photomultipliers, then you could see the Cherenkov light. It would be in ice, it's a sort of ghostly bluish glow. And if it was an electron or a tau neutrino, then the range is much smaller. So you'd see just a big blob that we call a cascade as opposed to a track. And several such detectors were attempted around the world. Some never worked, like Dumont. Some were in an interesting development phase, like Nestor. The ones that have actually worked and taken data, that is are Antares and IceCube. Before IceCube, there was Amanda, which was a prototype, and Baksan. And today we have the next generation experiments working, which is IceCube again in its full version. And meanwhile, in the Mediterranean, things have moved to the KM3 net, which has two sites, one off the coast of Marseille, where they're trying to build a detector similar in size to Antares called Orca, which will focus on neutrino oscillations. Another one off the coast of Sicily called Arca, which will be about 3 times as big as IceCube present is. And at Baikal in Siberia, they also are intent on building this GVD detector. And then there are, of course, what look like much smaller detectors by comparison, like Super K, but Hyper K is also, of course, in the pipeline. And this is a rather old slide. I have not shown everything here, but you get the picture that obviously you have to have a detector in both hemispheres if you want a full sky view. Now, this is IceCube. I'll skip very quickly through the pretty pictures because there are a lot of pretty pictures, and we send more every week from the people who are on shift there right now. So that's where the planes land on that track. and the people stay in a big building along with many other people who are there for other experiments. And you know it's the South Pole because a compass shows that all directions are north. Okay, and of course it's also bloody cold. Right now it's of course winter at the pole, and temperatures are pretty down, right? If including wind chill. Now, the IceCube Neutrino Observatory has 86 strings. I'm sure you have heard talks on IceCube before, who have told you that each of these strings carries 60 of these optical modules, 17 meters apart, and each module contains this photomultiplier, and that looks downwards. And one interesting innovation in IceCube was that our collaborator David Nygren at Berkeley, the guy who invented the TPC, he also designed the onboard digitization so that the signal is digital right from the dome all the way up to the surface and the data collection center, after which it is beamed back to headquarters and so on. So you can actually run this experiment from your laptop. When you take a shift, you can actually see the whole detector array right there on your laptop. It's a beautiful experiment. Now, this is 1 kilometer cube, that's a gigaton in terms of instrumented volume. And now we are, of course, taking data during construction, but even after construction finished, the 9 years have passed. So you have quite a lot of data. And it should be remembered that although this experiment was quite expensive to construct, it was about $279 million, but that works out to only about 20 rupees a ton, right? So it looks like, you know, it depends on how you look at it. And here is the obligatory photograph of the Eiffel Tower to show you the scale of it. Here at 2 kilometers, there is a layer of dust. So the detector is both above and below it. And the IceCube collaboration involves about 53 institutions in 12 countries. Hopefully, you know, there might be the possibility of India becoming involved at some point. There is a lot of interest among both theorists and experimentalists in India in this experiment. Now, the high energy neutrino detection principle I already alluded to. The neutrino interacts with the nucleus in the rock or ice, creates a muon or electron or tau, and that moves at superluminal speed and generates a Cherenkov cone with an angle of about 40 degrees. And you can detect that with these 3D array of sensors that we have there. And by determining the position, time, and amplitude of the hits, you can reconstruct the tracks. There's very sophisticated software for track reconstruction and timing, which allows you to determine what direction it came from and so on. Now, for a neutrino that is creates a muon, the direction is pretty well specified. It is less so for cascades because that's like more of a blob. And therefore, we have several classes of events. So the ones that are most easy to spot are these huge tracks. Remember, the scale of this is 1 kilometer. That's a very long muon track. Or you get these huge blobs triggered by either neutral current interactions, but their cross-section is smaller. So more likely charge current interactions of nu e or nu tau. The nu tau interaction could be a double bang because you might make an initial tau that then propagates a couple of 100 meters and then decays hadronically and creates another shower. So this has good pointing, but the energy determination is not so good because, of course, the muon escapes. You only get a lower bound. Here you get very good energy resolution, but very poor pointing. So essentially, you have to try every trick in the book to try to get as much information as you can out of these events. And thanks to the experimentalists on the collaboration who have made many, many innovations in this regard and are now using machine learning techniques to improve them still further, we have a detector that not only works fine, most of the DOMs that are put in the ice are still working and they're returning data. But what we mostly see with this detector are atmospheric neutrinos, because that, of course, is the huge flux that is created on those cosmic rays hit the atmosphere. I spent some time talking about these air showers. They not only create pions and muons, they can also create heavy flavors, charm particles, for example. And these are important because they have a spectrum which is harder than that of the pions and kaons and can mimic cosmic neutrinos. So we really need to know what the flux of these are. And for that, there is an interesting synergy with measurements that are being made of heavy flavor production at, say, LHCb, which in fact does scan a rapidity range which is pretty broad and can therefore directly put a constraint on charm production in cosmic ray showers. That's another example of the interplay between collider physics and astroparticle physics. Now, these neutrinos were, of course, as you all know, discovered in India, and this led on to the discovery of neutrino oscillations, which, of course, founded the field, was rewarded with the Nobel Prize, and so on. And it's interesting that this rusty-looking mine in Kolar, where this experiment was constructed by the pioneers in India years ago, led to this paper published on Independence Day, 1965, by these people from TIFR along with people from Osaka and Durham, and who detected these neutrinos. And they were nearly scooped, but actually by Fred Reines, who was doing a similar search in South Africa, but their paper came just 15 days later, right? And of course, we hope that this pioneering work in neutrinos in India would continue to continue today through projects like the India-based Neutrino Observatory. Now, when you want to look for neutrinos, which are coming from cosmic sources, you have to recognize that this downgoing flux of muons and atmospheric neutrinos is many orders of magnitude larger than the flux that you're looking for from astrophysical sources, right? The atmospheric neutrinos come from every direction. So if I look in terms of azimuthal angle, the direction, the angle with respect to the vertical. So this is looking upwards, this is looking downwards to the Earth. That is the North Pole if you are at the Antarctic. This is the South Pole. The downgoing flux of muons is, of course, absorbed by the Earth. You don't see muons to the other side, but the neutrinos, of course, come through. And also, some of these downgoing muons can be misreconstructed. So there's a huge background from them, already 3 orders of magnitude higher than even the atmospheric flux. So how are you ever going to detect these astrophysical neutrinos? Now, this is a huge challenge, and it occupied the collaboration for many years until people will realize that you can actually remove the atmospheric neutrinos if you remove the muons that come from the same cosmic ray shower, right? So this can only work for downgoing neutrinos, right? Because for upgoing neutrinos, Earth absorbed the muons already, so you can't actually use them as the trigger. And this technique was used in the so-called high energy starting events analysis, where you use the outer part of IceCube as a veto. So essentially, you are asking for an interaction to happen inside the detector with no activity in this bit of the detector that you sacrifice to use as a veto. Now, this means that your energy threshold is about 40 TeV. You can't see events below that. But you can then be sure that what you are looking for is in fact initiated by a neutrino and not an atmospheric neutrino, right? Because of the veto that you have imposed. Now, of course, doing so will also suppress your track-like events because you are, after all, throwing out all the muons. We also have an iStop, which is a surface array of Auger-like detectors, but right now it is not configured so as to act like a veto. In the future, we will have a surface array which is used as a veto. So you can see on this plot, which shows the events in the first 2 years of running, in a plot of the total charge versus the charge in the veto region. And when you see this, you realize that all that background that you are expecting from the atmospheric neutrinos is there. That's what you are mostly seeing. But if you look for events which have got almost no activity in the veto region, but a lot of activity inside the detector volume, then you can isolate this sample, and these guys are cosmic neutrinos. They're not atmospheric neutrinos. So this is, as I said, from the first 2 years of data, we are in the process of putting out the full 7.5-year data analysis, which builds on this. And this led to the discovery of cosmic neutrinos well, extraterrestrial neutrinos, which are high energy. And that then fits in here. So if you now look at the atmospheric neutrino flux, which has also been measured very precisely by IceCube, then at some point you start seeing a harder spectrum, and these are the cosmic neutrinos that you have been looking for. And you can see that these are well below the upper limits that had been set earlier. And here are the GZK neutrinos that you'd expect from the process that I discussed earlier. But you have not gone up to that point. You are only up to now about few PeV, say about 10 PeV, okay, which is still a very, very high energy. Remember that at accelerators, we have only studied neutrinos up to about 200 GeV. Now, the cosmic neutrino flux is already very interesting because it allows us to do some astrophysics. And in fact, since Sandeep asked me to talk about this, although this is not high energy physics, I very quickly mention that IceCube issues alerts on neutrinos that it sees to the whole astronomical community. And this was a very useful thing, because by issuing such alerts, we, in conjunction with other experiments, we are able to identify perhaps the first source of cosmic rays. To answer the question earlier, in September 2017, we saw a high energy muon track, and the telegram that was sent out to the astronomical community triggered responses from people working on Fermilat and MAGIC, gamma ray observatories, who also saw activity from that region. And thanks to, by combining the data, we realized that this was coming from a blazar, which was flaring. And this blazar also was detected in gamma rays up to very high energies by MAGIC. And there was a follow-up campaign. So thanks to all this, we were able to say with some confidence, not 5 sigma, but pretty high confidence, 3.5 sigma, that the high energy neutrino would have come from that activity in that blazar, and that blazar is at a pretty high redshift. And in fact, when you looked in the historical record of IceCube for neutrinos from that direction, we discovered that actually there had been significant flux from that direction, much more than you would expect statistically in the past. So combining the two pieces of data, we are pretty sure that this is a source of neutrinos. But that just, opened up a new can of worms. Why do we see only a very distant blazar and very luminous blazar? Should not we have seen more closer and less luminous blazars? And indeed, what are other objects that could also be giving such neutrinos? So this is an ongoing investigation with many multi-messenger partners. We also have MOUs with the gravitational wave detectors. So, that field is really advancing at a rapid rate. You would have had talks about it. Alerts, of course, are issued automatically in this regard. So let me now come to the actual topic of my seminar. Rajiv, do I have another 10 minutes?
Yes.
Okay.
Subir,
yeah.
Please.
Thank you. I'll speed up, but I'm sorry to have taken so long. But
No,
there were
please.
some.
Yeah.
Okay. So since we have this natural beam of neutrinos made in the atmosphere, for example, which are impinging on us from all directions, and we are situated at the South Pole, if we look through the Earth, we should see some attenuation of the neutrino flux at high energies, because at sufficiently high energies, even the Earth becomes opaque to neutrinos. We always talk about how neutrinos go through light years of lead. That is true for low energy neutrinos. At high energies, they start interacting like anything else. And we, of course, know the cross section because we have calculated it. So the degree of attenuation can be computed from that calculation and is shown here. And what we can ask is the pattern that we are seeing as we look in terms of zenith angle consistent with the absorption that is expected in the Earth? And for that, of course, we have to have a model of the Earth. We use the standard model, which is pretty good for the density of the Earth. Less is known about the composition. And the interaction length is typically of order the Earth's diameter at 40 TeV. So beyond that point, you would start seeing significant absorption. And we can actually do this with both atmospheric neutrinos and also the cosmic neutrinos, which go up to higher energies, because we know that most of them are extragalactic. So they should be also isotropic. So meanwhile, as I said, we have computed the cross-section at next to leading order. This was done using the Hera PDF, and we compared with the cross-section computed using other PDF sets like CT10 or MSTW and so on. And you can see that there are differences between them, but they're all consistent at around within 5%. Very recently, this has again been recalculated using NNPDF at next to leading order. That's a even more precise calculation. This has been done by Bertone, Gold, and Rowe. So now we have a measure of the cross section of the energies of interest. We can now ask whether the absorption in the Earth is consistent with the cross section, and the answer is yes. If I plot the cross section divided by the energy versus the energy, you know that at low energies the cross section is proportional to the energy, and then when the propagator of the W takes over, the cross section will fall down and it will go roughly as e to the 0.3. And we actually see that turnover in the data, which is this blue band here from IceCube. Okay, and this is inferred directly from the data, and you can see that our prediction is consistent with the data. Of course, the uncertainty experimentally is quite large. It's about 30–35%. So you cannot say much more than the fact that the standard model calculation is okay to within that uncertainty. But look at the energy. This is going up all the way up to 10 to the 6 GeV, whereas the laboratory experiments have only gone up to about a couple of hundred GeV, right? And therefore, this is entirely uncharted territory, and even a first measurement is very interesting. So this is a powerful probe of new physics, because of course you could have had any number of things which were affecting the neutrino cross section up to even these energies. And one example, for example, that was been discussed is the possibility of large extra dimensions at the TeV scale. That would have led to a dramatic rise of the cross section around there. Or if you had leptoquarks at the TeV scale and stuff like that. And in this plot, you can see that the existing data from IceCube plus an analysis of the cascades, which was done by Bustamante and Connolly, from whom this plot is taken, already puts interesting restrictions on new physics at the TeV scale. Of course, we were a few years late with this because LHC had already ruled out such things a little earlier. But now you can see the potential for using experiments like these to provide information that is complementary to the LHC detectors, because we can explore to higher energies. Okay. Now, an interesting test of this new physics is not just the overall cross-section, but the distribution of the inelasticity. That is called Y typically, because that depends on what kind of interaction the new physics is. Is it a hard interaction? Is it a soft interaction? And so on. Is it the excitation of lots of Kaluza-Klein levels, or is it like a hard photonic interaction? And or the formation of little black holes or whatever. Now, what you see here is a very nice analysis by Gary Binder, who did this for his thesis from the IceCube collaboration, who worked out the inelasticity distributions of the events and showed that they actually provide an excellent match to the expectation from the standard model, as is shown here. This is the Y versus the energy. And again, we are going to energies which are far beyond what can be explored in the laboratory. And there is pretty good agreement with the expectation. The uncertainties are, of course, still very large, but Gary kindly gave me a little forecast for what we could do with the 7-year data set. And you can see that you are actually getting to the point where you will be able to do some more precision physics. Of course, you need to compare with other calculations of the cross-section as well. Now, this is becoming important because precision is improving. The first measurement was 30% uncertainty, but hopefully we'll ultimately get to tighter error bars than that. So then you have to consider other issues. So for example, Vernon Barger and collaborators pointed out that at very high energies, you could actually make a top quark in neutrino interactions, right? So in the DigiLab evolution, you have to account for heavy flavors, and normally one accounts for, of course, the light flavors. But if you have to include bottom to top, if you go to sufficiently high center of mass energies, and that makes an important contribution. Also, of course, you could actually look for the formation of those top quarks in the IceCube detector if you were able to study exclusive processes. Now, we had actually already considered this. In an earlier paper, we had calculated the cross-section without the B2T splitting. And if you include it, and the difference is of order 20%. Now, both of these were approximations because when we included this, it was using a zero mass flavor scheme, which let me not go into technicalities, but there is some ambiguity in how to do that. And the real answer is somewhere in between these two. So you can see that there are theoretical uncertainties of order 10%. This issue has been recently revisited by, as I mentioned, Bertone, Gould, and Rojo, and they predict something which is in between. But it would be very interesting to see this top quarks in IceCube. Then you have nuclear effects. Now experimentally there has been very little hard evidence for this sort of shadowing effects. But if you look at PDFs in nuclei, then you find that the theoretical estimate suggests that there might be a drop in the cross section of about 5 to 10%. And here's an estimate of how much that might be. The uncertainties are very large, right? So you need more experimental input. This is, of course, important if you're, for example, talking about attenuation of neutrinos by ion in the Earth. Then there can be other contributions. You can have interactions of anti-electron neutrinos with electrons and atoms, not the nuclei, to create a W. This was first proposed by Shelley Glashow as a way to look for the W. And with a neutrino, you would need to have an initial energy of around 6 PeV, because we know the mass of the W. And this would be a sharp resonance, and this has been recently recalculated by Rory Gould, including all radiative corrections. Actually, I can't show it because the issue is still under discussion, but we have candidate events for the Glashow resonance. So watch this space, it will be published soon. Then we have radiative process, various kinds of Bremsstrahlung-like processes, Trident production, and so on. This can be important for heavy nuclei like iron, and there's a recent calculation by Zhou and Beacom, which improves on the previous calculation by Dave Seckel. So these are all things which can be up to 10% corrections. And these can become important as we go further and measure the cross-section and inelasticity more precisely. But let me talk about some new physics which is within the standard model, which is because we are exploring the very low Bjochen X regime of QCD. It has been speculated that in that region, since the gluon density is growing so rapidly, you might have a new phase of QCD, a color glass condensate. So, Wilczek and collaborators, Raju Venugopal and so on, have studied this in some detail. And it has some support from the heavy ion experiments both at Brookhaven and at CERN. Now, the geometric picture is that whereas you have a dilute gas of partons at high q square and high x, as you go to low x, in other words, large log 1 by x, you do get an increasing density of gluons, and that can cause the formation of this new phase of matter. And one interesting aspect of this is that this is expected to suppress the neutrino nucleon cross section below the standard model value, which we of course calculated in the on-screen limit. And this is where the experiment that I started this talk with comes in. So I showed you that the detectors of the Peierls Observatory can detect, in principle, neutrino-initiated air showers, which are coming very close to the horizon, because only a neutrino can come all that way and interact and create a shower. If it was a hadronic shower, then basically all that stuff would be absorbed on the other side of the Earth, and only a muon would come through. And in fact, we do see those muons in the flash ADC signals. Whereas if a shower comes from above us, then we actually see a lot more activity. So this is what a hadronic shower typically looks like. So if you see a shower from close to the horizon and it looks like that rather than just a muon, then it can only be due to a neutrino, because they can penetrate through the atmosphere and interact close to the array, right? So these are called young showers, these are called old showers. So you're looking for a young shower at a large zenith angle, right? And the rate of such events would be proportional to the cross section, obviously, and to the flux. But imagine another kind of event which is expected because of the equilibration of flavors that would be happening for neutrinos coming from a very large distance. About a third of the flux should be tau neutrinos. They can enter the Earth over the horizon, create a tau lepton, which at these energies would live for hundreds of kilometers, and create a shower which will emerge from the ground. And because the Auger tanks are above the pampa, they can have a little solid angle towards the ground and they can see these showers. So you can calculate how much sensitive area they have. And because these rate of these events is also proportional to the flux, but they are not proportional to the cross section, because if I raise the cross section, then there is more absorption in the Earth as well. So it turns out that effectively the flux, the rate of events is roughly independent of the cross section, because the two effects cancel. Sorry, I'm going a bit fast, but I have to get through the rest of the slides very quickly. So if you look at the expectation for the standard model cross section as a function of energy, and for the expectation of this quark glass condensate, this color glass condensate, which would be suppressed by a large factor at the high energies, what you can ask is, if we measure the number of quasi-horizontal events and the number of Earth skimming events, how many of each would we expect to see according to if you had the standard model cross section, or something which takes into account this BFKL summation, or a color glass condensate? You see, these would be on 3 different tracks. And we made an estimate that with a sufficiently large detector, this was supposed to be built in North America and it was never built, we could actually get enough events to tell the difference between these 3 cross sections. So this has not yet happened, but this is something to keep in mind for an interesting use of air shower detectors to do very fundamental physics to do with non-perturbative QCD, not any exotic stuff beyond TeV scales, but something that is happening at QCD scales, but at high densities. Then there is other unexpected physics that one might see in the standard model itself. Sorry, I didn't mean unexpected. It is, in a sense, it is expected, but the expectation of the rate is very uncertain, because you can also have exotic things happening in the non-perturbative phase of the weak theory that we have in SU2, because the ground state vacuum of SU2 is quite complicated. There are many minima which are distinct from each other. They carry different baryon and lepton number, and with a interaction that generates sufficient energy density, you might be able to trigger a transition from one vacuum to the other, and this least action trajectory is called the sphaleron. Effectively, it's like reducing a particle of mass around 9 TeV. That's the mass of the W divided by the weak coupling. And the rate for this process is 0 at normal collisions at the LHC, because it can only be mediated by instantons, and the rate for that is exponentially suppressed. It's negligibly small. But it has been recently suggested by John Ellis and company that this process might actually happen at a rate which is detectable. They are following a new suggestion by Henry Tai and Wong that this transition rate can be computed using a new block formalism. And if that is so, then the cross section for neutrino interactions would be much higher than the standard deep inelastic scattering cross section, and you would get amazing events in IceCube due to this, which these people say are likely to be high enough to be detectable, in fact, at a rate higher than in the LHC. So this is, of course, very speculative, but it just gives you a flavor of the kind of new physics we might actually find in IceCube, which is kind of different from the usual new BSN physics that you hear about. I don't have time to do justice to this plot, which has to do with what you can find out about new physics by studying neutrino oscillations over very long baselines and at a huge range of energies. So, of course, you know what neutrino oscillations are. It's a quantum mechanical process. And you can imagine a variety of things that can disturb neutrino oscillations and thereby change the final flavor ratio that you could measure. So you could have various violations of Lorentz invariance, equivalence principle. You could have decoherence due to interaction with quantum gravity effects, neutrino decay, non-standard interactions, sterile neutrinos could have an effect, new long-range forces, and so on. So the bottom line is that by measuring the flavor ratio, in other words, the fraction of electron neutrinos, muon neutrinos, tau neutrinos, we can distinguish in principle between the region of this parameter space that would be occupied by the standard model, given what we know about neutrino mixing so far. The uncertainties allow you to mark out this dark region. So anywhere within this dark region is consistent with three family neutrino mixing as we know it. And if you had the neutrinos that are coming from pi decay, then the final ratio should be here. If it is from neutron decay, it would be out there. Now, currently, with the 8-year data, we are somewhere here. And as we increase the amount of data with the Gen 2 extension, we would be able to pin down the flavor ratio much, much better and be able to investigate, therefore, a lot of this new physics. Okay. So this is a very, very exciting topic, and I've just given references to some recent papers to indicate to you how active this is. And this is certainly something for those among you who are interested in the topic to look at more carefully. So let me come to the end of my talk. I'm sorry I've gone over time. So neutrino telescopes have measured the deep inelastic scattering cross-section and inelasticity up to center of mass energies which are 10 times higher than are attainable at the LHC. No deviation from the standard model. Somewhat disappointing, but there it is. That also, of course, rules out new physics. It can change the cross-section by large numbers, but all these possibilities were actually already ruled out in run 2. Now, there might be new non-perturbative processes in the standard model, which can affect the cross-section at higher energies, like these electroweak sphalerons and this QCD color glass condensate. But in order to probe this, we'll have to go up to higher cosmic energies. Now, to do that, we have to have a bigger detector, and also to measure the flavor ratio more precisely, we'll have to have a bigger detector. So therefore, if you want to actually probe the energy frontier and use neutrino telescopes to study some of these new physics, we have to think even bigger than IceCube, right? I already mentioned KM3Net, the ARCA detector is planned to be 3 times as big as IceCube. IceCube's own proposed extension is called Gen 2. It's actually a pun because Gen 2 is also a kind of penguin. But this is the artist's visualization of what Gen 2 might look like. It's in fact a massive detector. It has the present IceCube detector is this bit here. Within that, we already are constructing the IceCube upgrade, which is a set of 7 very closely spaced strings, which will improve our reach at the low energy end for oscillations. And that is within IceCube. IceCube will be within the Gen 2 optical array, which is this big here. That will be about 8 kilometer cube. And the whole thing is under an even bigger surface array, which will have also a radio detectors. These are still under development. But when this is complete, and it is planned to start construction, as you can see from this timeline, in a few years and deploy in the 2030s. So this is relevant for the younger people amongst you. It is proposed to actually have a detector based on principles that have been shown to work well, analysis methods that have been very successful at teasing out the subtle cosmic signals from the data. And I'm confident that with the construction of this detector, we will be able to prove most of the new physics that I have discussed. But of course, with building a new detector, what is even more exciting is the things that we haven't talked about, the things that are truly unknown. And so I would like to end with this photo that I took of a menu outside a Greek cafe, which quotes the Greek philosopher Heraclitus, who says, "If you do not hope for the unexpected, you will not find it." Thank you. That's the end of my talk.
Thanks a lot, Shubirda, for your mesmerizing talk. And I'm sure that you could convince all of us that how these big telescopes are going to tell us if there are new particles, new interactions at those energies which we can't think of probing in our laboratories. So many thanks for this, covering the entire landscape in 1.5 hours. So now the floor is open for the questions to Shubirda. Especially I encourage young students, because this is a journey that is going to start now. He just mentioned that these big telescopes are waiting for us. So I'm sure you have questions. So please ask if there are questions.
What happened to that guy playing the music? He's gone.
Yes, we restricted him basically. So there are yeah. So there are some questions I can see. So maybe I can start one by one.
Please.
So Shubirda, there was a question from Mohammad Ful Hossein Sheikh. He's a student in Aligarh Muslim University.
Yes.
He is asking, why is the Cherenkov light bluish in color?
So this has to do with the property of the medium in which you are propagating. So effectively what it is a shock wave in a medium where the velocity of light is slower than your own velocity. That ratio of the two, the refractive index, determines the angle of the cone, and the actual color of the light is determined by the medium. You would have seen, even in water, if you have ever looked at a nuclear reactor. I once went to BRC and looked in a nuclear reactor. They had a training reactor. You see this bluish glow, which is coming from the Cherenkov light emitted by the escaping particles. Can we actually focus on questions relating to neutrinos?
So, okay, there is one question by Shadashiv that,
yes,
like GZK cutoff based on CMB,
yes,
is there any cutoff based on CNB, cosmic neutrino background?
Yes, indeed, and that would be at a higher energy, because the cosmic neutrino background, as you know, is colder than the cosmic microwave background. And actually, one of the plots, I actually showed a proposal, which was, let me go to that, which was actually, it says Z burst, if you can see this plot. This was a proposal by Tom Weiler that a very high energy neutrino could interact with a cosmic relic background neutrino close to us and create a Z boson in the center of mass. So you need a 100 GeV center of mass, and that would then look like a cosmic ray shower, right? The problem, of course, is that the cross section for neutrino-neutrino interaction is even at those energies is a lot smaller than for a neutrino for a proton interacting with a cosmic background photon. You need a high concentration of neutrinos, and the calculations show that although the neutrino, if they have mass, they would be more clustered around us than on the average. That clustering is by a very small factor. So essentially, the rate of such a process would be negligibly small.
But Shubirda, if there is this neutrino-neutrino interaction is happening,
yes,
then we may see some absorption in the flux spectrum, right? Like, because those neutrinos are gone.
That's right. So, and that's exactly what Tom worked out, that you would actually see features in the neutrino spectrum. But my point is that for a start, you would not be able to see such features in the neutrino spectrum unless you had thousands of events. You are a long way away from that. But we don't actually see the cosmic rays that should be created by those interactions, which should give rise to this Z burst. Because as you can see from here, the Z burst process should actually generate a lot of photons, high energy photons nearby that we have not seen. The limits are well below that.
And there are some new calculations also from by Mauricio Bustamante and his collaborators. They recently also wrote few papers on this when glacial events were not seen basically. So they were
Glacial events have been seen. So actually, I think part of the problem is that we are pretty data starved, as you have already gathered. And when we have a situation when we don't have that many events, you really need to have a good understanding of statistics in order not to prematurely believe that there are anomalies in the data when in fact there are no such anomalies. So if you look at this plot, this is the sum total of the cosmic neutrino events you have got. You can see how large the errors are. So you can always look at this and imagine that there are gaps in the data, there are changes of slope, there are cutoffs and so on. But actually, the bottom line, I can just say in one simple sentence, there are no such issues. Statistically, everything is consistent. And in fact, as proof of that, we have recently, we believe, seen glacial events and look out for a publication very soon on that regard.
So now there is a question from Professor Vivek Datar. So he is
Please.
asking, is there a possibility of using an acoustic signal for ultra high energy neutrinos?
Well, this was, of course, a very promising way that was investigated some time ago. And I'm aware of at least three such attempts. One was done from Rona in Scotland by a British group led by University College London, David Waters, who used a microphone that actually is used to detect submarines to hear showers making a sound. And then there was a experiment in the US and another one done in the Mediterranean. It turned out that that technique does not work too well in water. There is just too much interference, and it might actually work better in ice. Some people in IceCube seem to think so. But right now, the direction that is receiving most attention and collaborators is radio, not acoustic.
So, Subir, the question was basically motivated by the fact that if you want to increase the volume, then this might be a possible.
Yeah, of course, that was indeed the idea. But I'm saying that there has been a fair bit of R&D work done on acoustic already.
Okay.
I was not involved in that, so I can only give you the bottom line, which is that it is not. It has not turned out to be as a promising direction.
Subir, he has another question. What is the main source of uncertainty in the 3.5 sigma error for the 290 TeV event?
Oh, so there is, of course, there are several sources of uncertainty. You're talking about the TX event, the Texas event, as we call it.
The major part.
So
the AGN event, I think, right?
Yeah.
The blazer.
So okay, so let me try and bring that up. Sorry. Yes. So basically, you are asking what is the odds of an event that is associated with the gamma rays that were detected from a source there by Fermi and then also by the atmospheric Cherenkov telescopes within that time window. So you have to, of course, take into account that you are doing a blind search, and therefore you have to be concerned about the rate of false coincidences that you might get. Basically, the look elsewhere effect, right? And that gives you a significance for the. So it depends on what question you pose. What is your null hypothesis? That's what you're saying, right? The question that is being asked here is this neutrino that we saw associated with the blazer flare that was detected in gamma rays? Okay, and that therefore that source, because our pointing accuracy by itself is far too large. In fact, it's indicated, you can see here, this is the 50% error control. It's much too large to actually pinpoint the event. But the photon detectors, of course, can pinpoint it a lot better. The reason why we are convinced by this, in spite of this particular detection by itself not being that convincing, is that when you looked in the historical data in IceCube towards the same direction, we found that there had been an even bigger flare, you know, 3 years earlier.
Oh.
And that at that time there had been no gamma ray flare recorded from that direction. There was no alert. But when you look at the historical data, we find that that particular object has been throwing out more high energy neutrinos than you would expect by random from that direction. And this is a standard significance calculation for how unlikely that is to be a fluke. So when you combine these two separate 3.5 to 4 sigma detections, then the thing starts looking interesting enough that you want to publish it. But I will say that until we have more such sources and understand the answers to questions such as these, it is not yet a convincing detection of the kind that one might like to have in order to say that we have identified the sources of high energy cosmic rays.
Shubhendu, there is a question from Professor Shubhendu Rokit.
Yes.
Any update on high energy Anita balloon events?
Yes. So the Anita balloon events, as he knows, are coming up through the Earth. So if they were initiated by neutrinos, they would have to have a cross section for interaction much smaller than we calculate in the standard model. However, IceCube has done a search for neutrinos from the same direction at the same time, and we found nothing, right? So therefore, I think one needs to first settle the question of whether the Anita events are actually upgoing events or the reflection from the ice of an air shower which happened above the Earth. Now, the Anita collaboration, of course, has looked carefully at this, and they believe that the chances for the polarity reversing is very small. But I was recently made aware by some work by Alex Kuzengo and some glaciologists who believe that the ice layers might be much more complicated, and that there is some non-zero probability of that signal being faked by the reflection of an air shower due to a cosmic ray that happened above the Antarctic. And these are not neutrino events at all. So I think we really have to understand the systematic issues before, trying to understand what, those events from a physical point of view.
Okay, so no new events. Basically, that's all.
They have not published any new events so far.
Okay. Thank you, Subir.
Shubhendu, there is a question from Madhurima that what are the values of the mass and the lifetime of the super heavy dark matter?
Yes.
This is that she's talking about.
Well, so we were trying to understand the origin of cosmic rays, which are at energies of something like going beyond 610 to the 10 GeV. So of course you have to have a dark matter particle of mass more than that, and this particular one is for a particle of mass 10 to the 12 GeV, right? The reason why a supermassive particle like that is not entirely ridiculous is because, as I said, they can be created by the rapidly changing gravitational field during inflation. So if the inflationary scale is very high, say it's the gut scale, that's the highest it can be without generating too many gravitational waves, then the corresponding Hubble parameter is about 10 to the 14 GeV, 10 to the 16 squared by 10 to the 18. So you can make particles of mass up to 10 to the 14 GeV during gut scale inflation. And therefore, it looked like one could consider particles of that mass, right? And the lifetime would have to be very, very small because, of course, they are the dark matter, so they have not decayed away. In fact, it turns out that you need about just 1 in a million of these particles to decay, because the necessary lifetime is about 10 to the less than a million, sorry. The necessary lifetime is about 10 to the 8, 10 to the 9 times longer than the age of the universe. So less than 1 in 10 to the 9 of them have decayed by now.
Shubhendu, there are a couple of questions from Professor Monimala Mitra, who is our colleague here at IOP. So she is asking that, can IceCube distinguish between different BSM hypotheses?
Yes, well, depends on what we actually measure. So as I showed you, the cross section that we measure can distinguish between, say, something like dramatic, like 4 dimensions all the way, or new dimensions opening up at the TeV. This is an example. You can do it, but to do that, first you have to detect neutrinos of sufficiently high energy. We haven't got up to that point yet. We have only got up to about here, right?
Right.
So you would have to go another factor of 10 at least in energy in order to start distinguishing between, BSM physics, which is at a higher energy scale. So essentially, LHC has already ruled out new physics, as she knows, at energy scales up to a few TeV. And therefore, we cannot say anything more in that energy range. But in principle, we can prove up to much higher energies than the LHC if we have enough beam. But the flux at these energies is so low is that we need a bigger detector. We cannot do that with IceCube. We'll have to do that with IceCube Gen 2.
Gen 2.
Yeah.
She has one more question, that could you elaborate how much improvement the future upgrades can achieve? Like maybe you are talking about the IceCube Gen 2, maybe that is a good example to take, right?
Yes.
Well, depends on what particular aspect you are asking about. So as I indicated in this plot, which is actually taken from the Gen 2 paper, we put out a white paper recently,
Yeah,
and I think maybe
that paper
that's
is
very good. Yeah.
nice.
So that is already showing, for example, in measuring the flavor ratio, how much better will Gen 2 get compared to the current measurements, which are much bigger than this. Okay, so you can see here that in 15 years, by the time Gen 2 starts operation, we would have taken 15 years of data, and then 10 years of Gen 2 will be able to pinpoint the flavor ratio within this little yellow blob here. So these estimates have been made by people in IceCube using our known detector characteristics, systematics. These are informed estimates. They are not just a random line drawn on that plot. And one can similarly do estimates for how well one can do in measuring the cross-section and so on.
Shubhida, this IceCube Gen 2, all the
Yes.
Monte Carlos are ready. Like do we have really the idea how is it going to behave, like projection?
Well, obviously there is a great. You're extrapolating from what we can do currently, but obviously you can look at the scale of this project. Look, let me just say something. When IceCube was first built, the idea was to drill down. Well, the idea was to first drill down to about 1 kilometer under the ice surface. It turned out that was not good enough. There were bubbles in the ice, I'm told, I was not there at the time, which scattered the light too much, and the detector was not viable.
Bubble?
So, sorry?
It was a bubble in the ice.
Yeah, there were still bubbles in the ice. Now, the ice is under huge pressure, so the bubble should be forced out, but there were more bubbles than had been anticipated. So that is why IceCube is at such a huge depth. They had to go down much deeper than had been initially anticipated. So at that point, people might have given up. They might not have gone further, but they persevered and they went deeper and had the backing to do so. And therefore we have today a wonderful experiment. Now, when you are going to go another order of magnitude, it is hard to say that you have everything under control. Obviously, there will be many unanticipated challenges. The best you can hope to do is to be as prepared as you can be to meet them. And obviously, all the Monte Carlo's estimates are based on all the experience of IceCube physics over the last 10 years. But there would be, it started construction in 2004, as I said. And we have by now had about 10 years of data, finished construction around 2011. As new challenges come up, we'll just have to meet them. But one thing I can say that people in the experiment seem to be actually pretty good at meeting unanticipated challenges. And every experimentalist knows that nothing ever goes to plan. You have to be able to cope with whatever nature throws at you.
Sanjeev, can I ask a quick question?
Yes.
Just one question. You mentioned that the neutrino nucleon cross-section,
Yes.
people have considered the effects of sphelerons, non-perturbative processes like sphelerons. I
Yes.
just wanted to be clear that this is, when you're talking about instantons there, these are QCD instantons or these are electroweak instantons?
These are electroweak. So this is a calculation which has been, as I said, normally, as you know, the tunneling rate between those vacua is negligibly small. It is damped as e to the minus 1 over alpha or something, right? That's what you showed.
Right.
But the statement is, and this was first proposed by Andreas Ringwald many years ago, that in a high energy collider like LHC, you might have sufficient energy density at an interaction for sufficiently long that you could actually trigger a transition over the barrier on the saddle point. Now, the rate of that process has an exponential uncertainty, right? The energy is there, right? But the rate has a huge uncertainty.
Sure.
And the consensus has been, after a flurry of activity, I think it was in the 90s, there's a lot of activity and people tried to estimate it. And then I think there was a consensus that this process could not be detected, right?
Right.
Much more recently, Tai and Wong have argued that they have a calculational method to do this, which is and ascribed to Bloch. I'm not sure of the details, but adopting that, Ellis, Sakurai, and Spanowski say that they can now estimate the rate of such transitions in neutrino-nucleon interactions, and that rate is actually, look, it's not large. You're talking about a few events per year, but these events would be so spectacular that basically they would burn out our detector. So I hope these events aren't there. It's hard to imagine how anything could cope with such a dramatic thing. It's like, 128 Ws decaying together.
Yeah, I mean, I remember at that time, the Schiffman, Voloshin, these people had considered it, and they had shown that this non-perturbative process cannot actually happen in colliders.
Yes. So the interest was, you're quite right. The interest was that it might happen in the early universe in
High
a finite
temperature
temperature bath.
Right.
Yeah, that is the basis of leptogenesis and all that.
Right.
But as I said, this recent interest in this has been triggered by this observation by Tai and Wong, which I understand is not, it's under discussion. It has not been totally accepted by everyone. But it's interesting. Now, from an experimentalist point of view, I could say, look, this is totally unlikely. Or I could say, hang on, if there is even a remote chance that we might see something as amazing as this, it's worth having a trigger for it. That's all.
Right.
No, can I just extend a little bit, because you said that this process can the neutrino-nucleon process can also prove color glass condensate. That means you're also sensitive to QCD instantons.
Well, that is in a completely different kinematic range. The color glass condensate you're talking about is happening at, as I said, that is because we are probing such very small values of Bjorken X that the gluon density there is very large.
Are you sensitive? What I'm saying is, are you sensitive to QCD instantons also, in whatever regime?
You have to. Well, that is something worth thinking about. If you can think of an observational effect of those, yes, it is true that both are non-abelian theta vacuums, so you might have an effect due to that.
Okay, thank you.
Shubhita, there is a question from Poonam Mehta from JNU.
Yes.
She is asking that when should we expect results using radio detection techniques?
Well, Poonam, she's really better informed than I am about that. The truth is that...
Not really.
Okay. So radio detection is a long story, and it first started with attempts at radio detection of cosmic ray showers, not neutrinos, right? And we have had this ongoing for many years. It started at Karlsruhe on a small, the Cascadia array that they had there, and then it progressed to the Pierre Auger Observatory, where there were two groups trying to detect air showers with radio, and they did succeed. But as I understand it, they always needed a trigger from the ground array to be sure that what they were seeing was actually an air shower. Whereas to do what we are talking about, you need to be standalone, right? The radio itself should be able to determine if something is a air shower. Now, as we discussed in the context of Anita, that's exactly what Anita is trying to do. It is trying to detect neutrinos without the benefit of a coincident air shower. And that is difficult because they are also exploring new territory. They are seeing some exciting events, but that kind of raises new questions about whether the systematics in how radio signals behave when they're partly reflected by multiple layers of ice, is that understood, and so on, right? So currently, there seems to be a fair deal of confidence that radio detection will be viable and can be extended to the necessary scales in order to be a important component of, say, Gen 2, right? And I certainly know of many people who are working on it at the moment and who have done sufficient simulations to convince themselves that this is the case. But it is true that in the papers that I've seen published on radio detection of air showers, most of the detections were made, like 95% of them were made after a trigger was provided from the air shower. And I understand from talking to the experts that constructing a trigger for just the radio is very, very difficult. That is why the need a accompanying ground array would be good. But actually in Gen 2, we'll have the ground array as well. And I think even experiments like this one that I mentioned, which is to be built in, which is proposed for China, the ground array, that also now is thinking in terms of a air shower array.
Because until we just a small
Poonam, please.
so until we get to the radio regime, we will not be able to probe the very high energy end of neutrino spectrum.
This is true.
Cosmogenic, that is something which is kind of absolutely necessary.
Absolutely. And in fact, there have been, I can tell you about one experiment that was done from Groningen, where they basically looked with the radio telescope at the edge of the moon, because you would expect to see air showers in the periphery of the moon, right? And you would expect to see signals from that. And they actually didn't detect any, but that's because their threshold for that was so high that we don't even know if there are any cosmic particles at those energies, right? So sometimes you have to have the technique matching the astrophysics as well, because nature is not obliged to provide you a beam at the energies at which you can detect it.
True.
But the radio array that is proposed for Gen 2 is actually huge, and obviously a fair bit of development work is still necessary before you could claim that you have something which is as well honed a method as the optical method. The problem is that optical is just too expensive. These strings are spaced apart at 230 meters. They're far more widely spaced than in IceCube, because and they're using different PMTs, but they're still very expensive. That will be the most expensive component.
Related to this, Shubida, just now there is a question that, but with Anita, the HiCal air trigger is working, I guess. Is that effective enough for radio air shower detection?
Sorry, Anita is a balloon-borne experiment. It has no ground array of any kind. It just looks at radio pulses.
HiCal air triggers. He's talking about. So
well, I'm not an expert on the Anita experiment, but as I understand it, they look for radio pulses coming up from the ice sheet, and they look at the polarity of the pulse, and that allows them to discriminate whether these are due to the reflection of radio pulses from the Ascarian effect in air showers that are happening all the time above ground, or could they be signature of particles coming up from the ground. So I don't know what this trigger is that is being referred to.
Shubida, you have been talking for last 2 hours, but if you allow just 2 more questions, because
sure, yeah, go ahead.
So one is from Rothinda from Jamia Millia Islamia.
Hi,
Rothinda is asking, any specific B violating Phaleron transition process involving high energy neutrinos and other particles which you think could be verified?
Well, as I said, the only process we are talking about here is both B and L viating. It just conserves B minus L because that's the global symmetry of the standard model. And this Phalerons would be a probe of the non-perturbative, the complex structure of the SU2 vacuum. But as I already indicated, this is a long shot. Whether this can be detected or not is currently under discussion. There has been an encouraging estimate by these authors, and it is worth looking into further. So I would do that if I was interested in this question. But notice that to do this, you need an incident neutrino energy higher than 10 to the 8 GeV. So far, we have only detected neutrinos up to about, say 10 PeV. We have not got that far.
So maybe we can just take it as a last question, but there are many questions in YouTube, so we can forget about that. But now one last question, Subir. So this is from Sujata Pandey.
Yeah.
That to what extent the nucleon neutrino cross section measurement will improve with Gen 2?
Oh, okay. So what I showed you is the estimate that was made just using atmospheric neutrinos with IceCube. This is mainly using the absorption in the Earth, and it has a large uncertainty. Subsequently, there have been two other analyses using cascade events, and they are consistent with this, but the uncertainties are still large. Now, with Gen 2, obviously the errors are going to go down. So here you get an estimate of the uncertainties that you get from cascade events. This is not an IceCube analysis. The IceCube analysis is more refined, obviously. It uses the full detector simulation, but the uncertainties are still of order 30%. With Gen 2, you'll have a much bigger volume, which will essentially improve the event rate. But to actually progress better on this, what we really need is something that people are interested in doing, which is having a full Photon shower Monte Carlo. In other words, operate IceCube or Gen 2 essentially as we operate a collider detector. It is not just the cross section, but the individual channels that contribute to the cross section that become relevant. So, for example, processes like creation of tau leptons or top quarks, I indicated already that this is an interesting process that we could, for example, this formation of top quarks is something you could study. To do these kind of things and to measure the contribution to the cross section from that process, we would need to obviously be able to isolate such events, and to do that we have to have a more sophisticated event generator at the Photon level, next to leading order, etc. These are all things that we are planning at the moment, and people would like to set up such analysis frameworks in order to improve the uncertainty. But I think very optimistically, the uncertainty in the cross section is not going to get much better than 20%.
Okay.
But still, it is at an energy which you can never reach in the lab.
Right,
so
right. That
even knowing it within 20% is still enough to rule out lots of exotic things.
Actually, I saw an article after that Nature paper that we can now tell that how much dark matter may be there inside the Earth, or is it there or not, basically, right?
Oh, they just reversed so I can show you that. This is the paper that you're talking about.
Right.
All they did. Yeah, so it's a matter of what you take for granted. These people assumed that our standard model calculation is exactly correct, right?
And they reverse.
And they just reverse the argument. So then they infer the density profile, which not unexpectedly is perfectly consistent with PREM, right? So it's a matter of whether you put the error bars on the cross section or the error bars on the density.
It's a tomograph.
So there's nothing, yeah. But so if you knew the cross section very precisely, then you could do that. But and in fact, we would be able to do that obviously if we are able to calculate the cross section to say percent level precision, and that is happening in the standard model. In principle, you can do that if you take into account all the corrections that I mentioned. But some corrections are today quite large. So, for example, the correction I mentioned due to nuclear effects, you can see here it's already of order 10-15%, and this would be important for determining how much is the cross section on iron in the Earth. As you know, we have calculated for an isoscalar target that doesn't apply to the Earth. Yeah. So you would have to improve the precision of your cross section calculation to the necessary level as well. And then you have to take into account all these processes. Again, this photon mediated processes can be up to 10% of the you can see here 10-15% of the deep inelastic scattering cross section at high energies. So you have to understand these things better.
And this isoscalarity can differ in core, in mantle, or in crust.
Yeah, absolutely. So and we don't even know much about that, because whereas the density of the Earth is known pretty well apparently from seismology, the composition is not known that well.
From the mass and the moment of inertia of the Earth, we can
Yeah, so you could try to work that out, but obviously in any unfolding problem, you're trying to unfold what could be a very complex gradient of density and composition, and you have only a few moments of that distribution. So the unfolding is always unstable.
So, Shubidam, we have already taken.
Is there any other physics question that you can see that I can answer?
So I think it is a good time to stop, maybe because you have. I have to think for you. You have been talking for last.
No, that's all right. I don't mind. I mean, I'm glad there is so much
maybe
interest.
if there will be any, I will just email you. Okay,
Okay.
I'll try to make a bridge between you and the person who is asking.
Okay.
So what should I say? Shubida, thanks a lot that in this difficult time, you gave us time and you showed us the whole landscape peacefully with patience over internet. And I don't have any words to thank you. Basically,
there's no need for that. I'm very happy if I've aroused. I know already that there is a large community of phenomenologists in India and experimentalists as well who are interested in neutrino astronomy, and I very much hope that one day India would be involved in experiments such as this.
Right.
We can all unmute and clap, Sanjeev. We
Yes.
can all unmute.
Right.
Yeah,
Let
right.
us unmute. Let us all
Thank you.
unmute. We allow and clap for Subir. Subir, I don't know whether you have taken lunch, so you can have today a big lunch. You have spoken for 2 hours.
Well, okay.
Yeah.
Yes,
we are really
I'll be
grateful,
fine. Thanks.
and it was a mesmerizing colloquium, Shubida, and I will not
Thanks.
hesitate to approach you again because there is a series of natures from IceCube. So we are looking forward to it.
Yes.
And
So
I will bug you again.
Sure.
Again. Yeah.
So please watch this space for the Glashow event paper, which will hopefully come out soon,
Right.
and for the 7.5-year analysis of the starting events, and several papers two of our papers have just been accepted in PRL on oscillations.
Right.
It is a really exciting experiment, I have to say this.
And I like
And
the
yet-
IceCube Gen 2 review, the review
Yes.
that came up.
Yes, but
last
please
week.
remember that the whole business nearly got scuppered at the beginning because of unanticipated experimental difficulties. Experiment is very hard. I'm not really an experimentalist, but I'm enough of one to appreciate just how hard it is. So let us also spare some thought for our experimental colleagues who have to do the hard work.
So let's have a
Thank
big
you.
cheers for IceCube. Again, we can have a big cheers for IceCube.
Thanks.
Okay.
Thanks.
Yeah.
Okay, bye then.
So, okay, Shubida,
Thank you.
thanks a lot.
Not at all.
With these words, I'm signing off, and have
Okay,
a great
okay.
day with full lunch.
Thank you.
Yeah.
Thanks.
Big lunch.
Okay. Okay, thanks.
Okay.
Bye.
Shubida, thanks a lot. Bye.